While the world was fixed on the heavyweight showdown, Tesla versus BYD, battling over who could build EVs with more range or slash prices faster, something massive, something nobody saw coming, was quietly taking shape behind closed doors. A company you already know, a giant of the auto industry, General Motors or simply GM, was deep in the shadows, working on a technology with the power to not just disrupt, but potentially annihilate the entire landscape of transportation as we know it. And now the curtain is finally beginning to lift. GM has reportedly unveiled an engine unlike anything on the road today. It's not electric, yet it produces zero emissions. It doesn't burn petrol or diesel, yet it promises a new kind of power. It shatters the perceived boundaries between the two worlds we thought were our only options. This isn't just some minor engineering tweak. This is a fundamental shift in thinking, a concept so radical it could render both electric vehicles and the traditional internal combustion engine obsolete. Many experts are whispering that this could be GM's ultimate checkmate, their biggest gamble and potentially their most monumental triumph. If this technology succeeds on a grand scale, it won't just redefine cars. It could send shockwaves through the entire global energy sector. The burning question echoing through the industry is this truly possible? Can a dark horse like GM, with this mystery tech, truly swoop in and claim victory in the race everyone thought was only between Tesla and BYD? For years, GM has been searching for an answer beyond the electric vehicle. They needed something not only kind to the planet but also capable of tackling the major pain points of EVs: their limited range, the high cost of batteries, and the dependency on charging infrastructure. In this intense search, they stumbled upon a forgotten glimmer of hope buried in history. A technology far older than the car itself, often overlooked, sometimes even dismissed. They found new potential in the power of compressed air. Now, if that sounds surprising, you're not alone. Using air as a source of energy isn't some brand new concept conjured in a Silicon Valley lab. Its roots stretch back to the late 1800s. Believe it or not, cities across Europe, most notably Paris, actually utilize this very technology to power trams and even equipment in mines. It worked. It was clean for its time, but ultimately, it couldn't compete. As petrol and diesel engines roared onto the scene, proving faster, more powerful, and more easily scalable for the emerging automobile age, the quiet potential of air, power was sidelined, fading into obscurity. There was a brief flicker of a return around 2010 when the French automaker Peugeot took another look. They saw the potential and tried to combine compressed air technology with a conventional engine, aiming for a hybrid system that offered eco-friendly performance without the burden of heavy batteries. It was intriguing, promising, but for reasons that remain murky, that experiment never truly made it out of the testing phase. It just stopped. But where others failed or simply gave up, GM saw a different path. They looked at this neglected technology and recognized something profound. If developed correctly, if the inherent limitations could be overcome, it wasn't just an alternative to EVs, it could fundamentally change the rules of the game for the next century. And so, while the rest of the automotive world was charging headfirst into the electric future, GM made a strategic decision. They went quiet. They began their research and development in secret, away from the spotlight, investing heavily in this overlooked potential. Now that they're pulling back the curtain on taking this technology in a radical new direction, the critical question looms. Does it genuinely possess the capability to eclipse both electric and traditional fuel-based systems? So, how exactly do these proposed compressed air vehicles work? If you're picturing something similar to a battery setup or a petrol engine under the hood, prepare for something quite different. Their mechanism is both distinct and remarkably simple at its core. Forget burning fuel. Forget the weight and complexity of massive battery packs. The power in these vehicles comes purely from the pressure of air. Yes, they operate using a special type of engine known as a compressed air engine, or sometimes called a pneumatic engine. From the outside, it might resemble a conventional engine block. Pistons, cylinders, valves are all present. But the internal operation is where the magic happens. There's no spark plug igniting fuel, no explosion driving the piston. Instead, highly pressurized air is released into a chamber. This sudden influx of high-pressure air forcefully shoves the piston forward. A spring then pulls the piston back once the air is released. This rapid back-and-forth movement of the piston is converted into rotational motion, ultimately turning the wheels and propelling the vehicle. The beauty? Zero smoke, zero toxic gases. Just pressurized air doing the work through mechanical efficiency. What makes this particularly interesting for a company like GM is that the basic design principle shares similarities with traditional engines. This is precisely what allowed them to see the potential for rapid development, potentially leveraging existing technical know-how and manufacturing infrastructure rather than building entirely new systems from scratch, as was required for EVs. Now that we have a grasp of the basic mechanics, the next crucial question emerges. What makes this compressed air engine so potentially revolutionary, so different, and perhaps better than both electric vehicles and petrol engines? Let's start with its most compelling attribute. It's 100% pollution-free. This technology doesn't combust any fuel. It doesn't release smoke, greenhouse gases, or any toxic emissions whatsoever. It simply uses the air that surrounds us every moment, puts it under pressure, and releases it back out, unchanged. This means a vehicle running on compressed air has no direct negative impact on the environment from its tailpipe, because there isn't one. But the advantages might not stop there. There's another significant benefit, often understated, hidden within the simplicity of the design: cost. Think about electric vehicles. They rely heavily on rare earth metals like lithium, cobalt, and nickel, materials that are not only scarce but also expensive to mine and process. Compressed air engines, by contrast, are not dependent on any of these. They are constructed using far more common and cheaper materials. This translates directly into a potentially much lower manufacturing cost per engine, making the vehicles themselves more affordable for the average consumer. And it's not just about the material cost. The production process itself is far less complex. Since these engines don't deal with the extreme heat and combustion pressures of burning fuel, they don't require incredibly strong or heavy-duty metals. This allows for the use of lighter materials, which not only reduces the overall weight of the vehicle, improving efficiency, but also makes the assembly process quicker and less resource-intensive. There's also a subtle but crucial point often overlooked in the EV discussion: the source of the energy. While electric cars are emission-free, at the point of use, the electricity they consume often comes from power plants that burn fossil fuels like coal or natural gas. Compressed air engines, particularly if they can be powered by localized renewable energy sources or even regenerative braking systems, emerge as a potentially cleaner and more truly independent energy option, less tied to the existing, often fossil fuel-dependent grid infrastructure. When you look at operating costs, compressed air engines present a truly compelling case. Imagine never having to stop for petrol again. Imagine no waiting in line at charging stations. The fuel is literally all around you, available everywhere. It simply needs to be compressed and stored, and the engine runs. There are no complex chemicals being burned, no precious metals consumed in operation, and, as mentioned, absolutely no toxic fumes emitted. And perhaps the most elegantly simple part: the air that goes into the engine comes out in exactly the same chemical composition it went in. There is zero waste. It's difficult not to look at this and feel like you're witnessing the potential blueprint for a truly future-proof technology, one that addresses environmental concerns, cost barriers, and energy independence all at once. But, as with any truly disruptive idea, there are two sides to this coin. While the potential simplicity and cleanliness of compressed air technology are undeniably attractive, it has historically faced some significant technical hurdles that have prevented its widespread adoption. The first and arguably biggest limitation has always been the relatively low energy density of air compared to liquid fuels like petrol or the energy stored in modern batteries. Put simply, air, even under high pressure, doesn't pack the same punch. As a result, to generate useful power, the engine has to spin incredibly fast, at very high RPMs. This leads to increased wear and tear on the moving parts, making durability a concern. Furthermore, the torque, the rotational force that gets a vehicle moving from a standstill or helps it climb hills, is historically very weak in compressed air engines. This makes them less suitable for demanding tasks like hauling heavy loads or navigating challenging, uneven terrain. Another challenge? Lubrication. Conventional engines use oil circulated with the fuel or through a dedicated system. Compressed air engines don't have this natural lubrication process from the fuel itself, presenting an additional maintenance consideration. Adding to the challenge was a very real and terrifying concern: safety. Many of the early attempts at compressed air vehicles used ordinary steel tanks to store the high-pressure air. These tanks were incredibly heavy, adding significant weight to the vehicle and slowing it down. Worse, they were inherently dangerous. If the tank were to suffer an impact in a collision or even develop a structural flaw leading to a leak, the immense pressure contained within could cause it to rupture or even explode with catastrophic force. To be brutally honest, driving one of these early concepts must have felt remarkably similar to sitting inside a moving pressure cooker, just hoping it didn't burst. But this is where GM claims to have potentially rewritten the script. GM didn't just look at these challenges. They reportedly dove deep into them, determined to find radical engineering solutions. Their reported advancements begin with the air storage itself. They haven't just improved the old tanks, they've replaced them with a new generation of ultra-high-pressure air containment systems. These new tanks are said to store air at pressures significantly higher than anything previously attempted in vehicles, effectively doubling or even tripling the energy density delivered to the engine's cylinders. The reported result? Performance. Metrics that GM believes are approaching, or even matching, those of petrol-powered cars, particularly for acceleration and city driving. While the torque might still be a work in progress compared to, say, a V8 engine, GM suggests it's more than adequate for the demands of a typical urban vehicle. But GM's truly audacious move, their potential stroke of genius, lies in a completely different approach to storage. Instead of simply putting a tank in the car, they reportedly designed the entire structure of the vehicle to be the tank. Yes, the chassis itself functions as a massive, integrated air storage system, and this isn't the return of those heavy, explosive steel nightmares. GM is said to be utilizing cutting-edge, lightweight yet incredibly strong composite materials. Think special fiber-reinforced thermoplastics, the kind of stuff used in aerospace or high-performance racing. This not only drastically reduces the car's weight compared to carrying separate heavy tanks, but, crucially, these composite structures are designed to be far safer in the event of a collision, flexing or dissipating energy rather than rupturing explosively under pressure. So, if GM's claims hold true, you could soon be driving a car that is lighter, potentially faster in urban environments, and engineered not to become a ticking air bomb in an accident. If these technical breakthroughs are real, if GM has genuinely solved the historical limitations of compressed air, this could indeed be the inflection point where the long-dormant dream of air-powered cars finally moves from science fiction closer to tangible reality. This leads us to the critical question hanging in the air. When will this technology actually hit the streets? When could we realistically expect to see vehicles gliding along powered purely by the air around them? Providing a precise timeline is inherently difficult. but based on the reports of GM's intense activity and the seriousness with which they are reportedly pursuing this, it's suggested that this technology could reach a production-ready stage within the next few years. These aren't just theoretical concepts being toyed with in isolated laboratories. GM is reportedly investing significant resources, actively tackling the remaining challenges like maximizing torque, extending range for highway driving, and refining the integrated safety systems. This doesn't feel like a speculative side project. It appears to be a meticulously planned, long-term strategy. GM is positioning itself not just as a participant in the next era of automobiles, but as the potential leader of a completely new paradigm. And make no mistake, for GM, this isn't solely about environmental sustainability. This is a shrewd, high-stakes business masterstroke. They understand that the era of the internal combustion engine is drawing to a close. They also recognize that they are currently playing catch-up in the established electric vehicle market, currently trailing behind key competitors. In this precarious position, discovering and perfecting an entirely new, third way that could potentially leapfrog both EVs and traditional cars could fundamentally alter the competitive landscape and secure GM's dominance for decades to come. Now, if you're wondering if this scale of ambition with compressed air has been attempted before, the answer is complicated. While the core tech is old, a major automaker attempting it on this scale, with these proposed solutions, is largely unprecedented. As mentioned earlier, about a decade ago, Peugeot developed that hybrid version of their 2008 model, combining a traditional engine with compressed air assist. It was an interesting concept, aiming for impressive fuel efficiency by using air power at lower speeds. Initial tests were promising, with claims of achieving fuel economy figures reportedly around 120 miles per gallon, a number that, at the time, seemed like a bigger breakthrough than many pure EVs or hybrids were offering. But then, something puzzling happened. Peugeot abruptly and quietly shut down the entire project. Their official statement was simply that the plan was not economically viable. Yet, when a technology shows such potential for fuel savings and eco-friendliness, that explanation feels incomplete. It raises questions. Could there have been other factors at play? Was the project deliberately halted for reasons beyond simple profitability? If we dig a little deeper into history, disturbing parallels and stories of potentially suppressed energy technologies have surfaced before. Consider the case of Stanley Meyer in the 1990s. He claimed to have developed a water fuel cell that could theoretically run a car using water as the fuel source, breaking down water into hydrogen and oxygen on demand using minimal energy. When he began to make his invention public and attract investor interest, rumors suggest he came under intense pressure from powerful entities, particularly those with vested interests in the oil and gas industry. Reports claim he was urged, even threatened, to disavow his technology, to declare it a hoax to avoid shaking the foundations of the existing energy empire. But Meyer reportedly refused to back down. He continued seeking investors to bring his technology to the world. Then, on March 20, 1998, during dinner with two potential Belgian investors, Meyer suddenly ran out of the restaurant. His last words before collapsing, according to reports, were a desperate shout, "They poisoned me." He died minutes later. The official cause of death was later ruled a brain aneurysm, but the circumstances fueled intense speculation and conspiracy theories. Adding to the mystery, immediately after his death, Meyer's workshop was reportedly raided, and his water fuel cell engine and all known prototypes mysteriously vanished. It's easy to dismiss such stories as mere coincidence or paranoia, but when a potentially world-changing technology emerges, one that threatens existing power structures and trillion-dollar industries, and its inventor meets a sudden, dramatic end, followed by the disappearance of the technology itself, it inevitably makes you wonder. History, it seems, whispers tales that obstacles to radical innovation aren't always just technical. Sometimes they are silent. Fierce battles waged between political power, economic empires, and corporate interests determined to protect the status quo. For GM, then, this isn't just an engineering project, it's also a potential battleground. A fight for a potentially sustainable future against the deeply entrenched systems built on existing energy sources. If GM is truly making this monumental pivot towards compressed air, they must surely be doing so with extreme caution, perhaps even maintaining a level of secrecy far greater than they let on. The cautionary tales of Peugeot's unexplained abandonment and the tragic, mysterious end of Stanley Meyer serve as stark warnings. Moving too openly, too soon, with a technology this disruptive could invite opposition that is not only technical but potentially existential. Despite the historical shadows and potential future challenges, GM's current global position is undeniable, adding immense weight to any major strategic move they make. The year 2024, mentioned in some reports, was particularly significant for General Motors. While the global spotlight focused intensely on the EV arms race between newer players like Tesla and BYD, alongside traditional rivals like Ford, GM was quietly solidifying its massive footprint. They remain the undisputed leader in the crucial American market. Reports for 2024 suggest GM sold approximately 2.7 million vehicles in the U.S. alone, marking their strongest sales performance since 2019 and maintaining their position as America's top-selling automaker. Globally, GM sold around 1.36 million vehicles in that period, showing steady growth even as sales fluctuated in certain regions like Europe. Their 16.5% market share in the U.S. signifies a powerful, established presence. Crucially, GM hasn't ignored the EV wave entirely. They've also made significant strides in the electric vehicle segment. Reports indicate they sold around 42,000 EVs in 2024, a notable 50% increase over the previous year. This clearly signals that GM is diversifying, not content to rely solely on petrol and diesel. Vehicles like the Chevy Equinox EV reportedly became a bestseller in the electric SUV category in the U.S., moving over 28,000 units. While Tesla still holds the global EV crown, GM has strategically grown its EV market share in the U.S., reportedly climbing from 6% to 9%. Another immense advantage GM holds is its sprawling, established production network. Unlike newer competitors who rely on a few major gigafactories, GM possesses a robust, deeply integrated manufacturing system spread across the United States, China, Mexico, and numerous other countries. This global footprint gives GM significant advantages in terms of production speed, scalability, and cost control, factors essential for bringing any new technology to market en masse. Beyond manufacturing, GM has also been heavily investing in core EV technologies, including software and battery research. Their new Ultium battery platform is designed to be modular, lighter, more durable, and capable of faster charging. This technology is slated to power future GM EVs across all segments, aiming to directly compete with Tesla's established lead in battery range and charging speed. GM has publicly stated intentions to introduce EVs in virtually every vehicle segment, SUVs, sedans, trucks, by 2025. What's fascinating about GM's position is their unique dual expertise. While Tesla is almost exclusively focused on electric vehicles, GM possesses deep, decades-long experience in both internal combustion engines and now rapidly growing expertise in EVs. This dual knowledge base potentially gives GM unparalleled flexibility to adapt quickly to market shifts and consumer demands, understanding the engineering challenges and consumer expectations of both worlds. While Tesla excels in social media presence and building a cult-like brand following, GM seems to be executing a quieter, more pragmatic long-term strategy. They are not just launching entirely new EV models but are also reportedly preparing electric versions of their most popular established vehicle lines, leveraging existing brand loyalty. This multi-pronged approach underscores GM's commitment to transitioning towards a zero-emissions future, but potentially one that includes more than just batteries. In summary, General Motors remains an automotive powerhouse, especially in the United States. Their recent growth in the EV segment clearly signals their readiness to challenge established players head-on. But the whispers about their secret compressed air engine project add an entirely different dimension to the narrative. It suggests a potential future where the energy debate isn't just about petrol versus electric. It could be about something far simpler, far cleaner, and potentially far cheaper: air. GM claims to have overcome the historical technical hurdles, potentially unlocking a technology with zero emissions, low cost, and independence from scarce resources and power grids. Yet, the historical shadows of abruptly halted projects and inventors meeting tragic, mysterious ends linked to disruptive energy technologies cannot be ignored. The question isn't just whether GM can perfect this engine. It's whether the powerful forces invested in the existing energy landscape will allow it to see the light of day without a fight. What does GM truly have up its sleeve? And can they navigate the unseen obstacles that have reportedly scuttled similar disruptive innovations in the past?